Okay, let's talk for a minute about figuring out the equations for relationships from graphs. Over here on the right-hand side of the screen, I've written the four accepted equations that describe kinematics, motion. The top one is just that average velocity is equal to the distance traveled divided by the time. The acceleration is equal to the final velocity minus the original velocity divided by the time. The distance traveled for an accelerating object is equal to 1/2 multiplied by the acceleration times time squared, and that the final velocity of an accelerating object is equal to whatever its original velocity squared is plus 2 times acceleration times the distance traveled. Now, over on the left-hand side here, I've got three axes for graphs, and there are three common generic relationships that show up a lot. If you have a direct relationship or a linear relationship, the best fit line ends up looking like this. And the equation that describes that shape is just y is equal to some constant multiplied by x. So whatever value you have for x, if you know what the slope is, the constant, you can multiply those and you can calculate what the y quantity would be. The second really common one, you'll end up with a relationship that looks like this, and that indicates some kind of an inverse relationship, where as the x variable gets bigger, the y variable gets smaller. And the generic equation for inverse relationships is y is equal to some constant divided by x. And then you often have a curve with an upward indication of some kind, either like this or like this. And the generic equation for those exponential relationships is your y variable is always going to be equal to some constant multiplied by your x variable raised to some power. And that's supposed to be an n raised to some power n. And that n is usually either a 2 or a 0.5. If it's at 2, that's indicating you've got a squared relationship that produces this curve. If it's a square root relationship, then that power is 0.5, and that produces this curve that's shaped like that. Now, in this graph where we're analyzing the motion of things, the first one we plot out, or the first graph we plot out, is the relationship between distance and time, where time is your independent variable and the distance traveled is your dependent variable. Now, one thing that can cause confusion here is that in our symbols that represent motion, x, like this, represents the distance traveled, and that x and this x is not the same x. This x means distance traveled. This x is just the generic symbol for the independent variable. In this case, the distance traveled is our dependent variable, and so this x goes right here. So we've got this distance versus time graph. So x versus time for constant velocity motion. And when you do that, when you plot that out, you get a graph that looks like this. Well, the generic equation for that linear relationship is this y equals k times x. So the generic expression is y is equal to kx. Now, when you plot this out, you'll find the actual slope of the line, so you'll know the value of this constant. If you use graphing software like Logger Pro, it'll tell you that. But anyway, you find that constant, and that value of that is what goes in here. So the specific equation, you take your y variable, which in this case is x, substitute in for y right here, is equal to the constant, and I don't know a value for the slope on that first set of data, so I'm just going to leave the symbol to be a k. But if you know the value of the slope, you can put that number in. So it'd be multiplied by a constant, multiplied by your x variable, and your x variable here is time. So the specific equation using our symbols plugged into this y equals kx becomes x equals kt. Then the accepted equation for this, we go up and we look at our equations that describe kinematics, and we've got this one that v is equal to x over t. Well, if we algebraically rearrange that and solve it for x, it would look like this. X is equal to v bar times t. And notice that when it's in this form, that's essentially the same thing as our specific equation here. So x is equal to v bar multiplied by t. So that is our accepted equation. And it shows us that the significance of this slope, the slope of that line corresponds with v bar. The slope of that line is the average velocity of the object. Then, if we take a look at our second graph, in our second graph we look at accelerated motion, and we plot out the distance versus time graph, and you get a shape that looks like that. Well, the generic equation for that shape is y is equal to k multiplied by x raised to a power. And specifically, this one is a squared relationship. So y is equal to kx squared. Then, for the specific equation, if we substitute our y variable in here and our x variable in here, this becomes x is equal to some constant multiplied by t squared. Then for the accepted equations, we go up here and we look at our equations that describe motion, and we've got this one that's actually already solved for x right here, and it is x is equal to 1/2 times a times t squared. And so again, it shows us the significance of this constant is that constant is equal to 1/2 of the acceleration. So if you know what the acceleration is, 1/2 of that quantity times t squared will tell you the distance traveled. Then, if we go a little bit farther, we plot out this graph for constant velocity motion, and we plot the velocity versus time, and at constant velocity motion we get this horizontal line that looks like that. With straight line, again, it's a linear relationship where y is equal to kx is the generic relationship. In this case, the slope is 0. The k isn't changing. So the specific equation then, when we substitute things, is equal to v is equal to some constant multiplied by t. And if we look at our accepted equations over here again, if we notice this one that defines acceleration, where acceleration is equal to the final velocity minus the original velocity divided by the time, if I rearrange that one to solve it for final velocity, it is final velocity is equal to original velocity plus at. And in this case, since the acceleration was 0, 0 multiplied by any amount of time, that whole thing is equal to 0. And basically it tells us that if the acceleration is 0, the final velocity will be equal to the original velocity. And that is our accepted equation. Vf is equal to v original plus at. And in this case, the a is the acceleration of 0, and the constant here is the velocity. The final velocity and the original velocity are equal to each other. They're a constant. If we go forward and look at the last graph then, where we're looking at accelerated motion and we do velocity versus time, again we get a linear relationship. So the generic equation for a linear relationship is y is equal to kx. When we substitute our variables in, our y variable is velocity is equal to some constant multiplied by our x variable, and our x variable is t. And this one, the equation, the accepted equation, turns out to be the same one as the last time. It is vf is equal to v original plus at again. In this case, the original velocity was 0, and so it just simplifies to the final velocity is equal to the acceleration times the time. And in this case, the significance of the constant is it tells us what the acceleration is. So that's how you go from a generic equation to comparing it to an accepted equation and seeing what the significance of the constant in the equation is.